Okay, so thanks for coming out today. I'm really excited to speak about time series modeling. It's a topic I really enjoy. I think it's fascinating, and it has a lot of real-world applications. So I've used time series modeling a lot on my own in projects, class projects, as well as in my internships. I wanted to share it with you guys. Yeah, help yourself to some pizza. They're just coming in. So really, like, the goal of this lecture is to introduce you to some key introductory concepts in time series modeling. Right now, there's a lot of craze of very complex models to model sequential data. But I want to start out just by introducing the basics, because a lot of the properties learned about regular data, like independence, for example, doesn't carry over to time series. And there's a different way, we have to find different ways for modeling time series because of that. And then, so I'll cover some of these basic things, like, what are some key properties and some, major theories for time series data? How do you describe, measure, and remove things like trends and seasonality, which are very common in time series data? I want to explain the concept of stationarity a bit, which is also very important. We'll touch on autocorrelation a bit. And then finally, I'll introduce you to one brand of forecast called the ARIMA models. This is a forecast, a time domain method for forecasting. And I'll show you how you can create your own time series forecast. But as you can imagine, there's a whole host of ways to model time series data. And this is just showing you one way to do it. But hopefully after this lecture, you'll have all the skills to learn a new forecasting technique on your own. So we'll start by discussing some of the properties of time series data, things like what is trend, what is seasonality, what does it mean for a series to be stationary. Then we'll move on to applications and examples. So we'll discuss 4 key applications of time series modeling. And we're going to dive into 2 of those applications. And those applications will be driven by an example. And then we'll move on to descriptive methods for time series analysis, right? So how do you measure properties such as trend and seasonality? How do you remove those effects? And then finally, once you've done that and your data is prepared for forecasting, we're going to discuss the ARIMA forecasting method. Right. So first, the basic thing. What is a time series? A time series is basically a sequence of observations over a period of time. So a very simple time series, or maybe not that simple, is the heart rate. So this is actually not heart rate. This is the ECG graph, which measures heart activity, so like the electrical activity of the heart. And the way we talk about time series data, the notation, is that we have these observations, x1 through xn, where xt is the point observation. So it's an observation at time t. So there are many different ways of thinking about this. How do you sample time series data? There's one way in which we have what's called a point process. So a point process is data is coming in, but you don't know ahead of time when it's coming, right? So maybe you're trying to measure when a bus is arriving at a bus stop, right? So, and this is the time. So bus can be arriving here, 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 and you have no idea. But what we'll be considering in this lecture is time series with equally spaced observations, right? So in this kind of time series, we have observations at equally spaced timestamps, right? And this will make it much easier to model the data. Although you might imagine if there's some things that may not be, equally spaced observations, right? So imagine an example like rainfall, right? So you don't get rainfall every day, but it'll come in as a point process, right? On some days you'll get rainfall, and some days you'll have sunny days, right? But let's say you want to sample the rainfall. What you could do is you could aggregate the rainfall over a month. You can sum it up, and then sample per month, right? So just because your data is a point process doesn't mean you can't convert it to a discrete, evenly sampled timestamp like this. Cool. So one major property of time series data is that each observation in a time series is dependent on all of the other observations. right? So you can imagine if you have some process, right? It's partly dependent on the previous values in the process, and then partly depending on its current environment, right? This is clear in the ECG graph, right? So we see there's some peaks and there's some valleys, right? And you see like order of that data, right? You see like there's a peak and then a valley, and then kind of it's steady for a while. And it's a very important property of time series because not all data has this dependence property, right? So all of the models that you've been learning in class so far, we made the assumption that the observations were independent, right? So the features could be dependent on each other, but the observations itself, the samples were independent observations, right? But in time series, that assumption doesn't hold. And so we can't really fit a simple linear regression model to a time series data. We will do a flavor of linear regression. We have to do some adjustments to it. But we can use the previous statistical models that we've learned so far. Particularly, it's important to, in any kind of modeling, time series modeling approach, to account for the time order of the data. And you'll be seeing that time order incorporated in all the models that we discuss. So any question about this dependence property? So now let's move on to some more properties of time series data, specifically trend and seasonality. So these trends and seasonalities are very common. They happen in all kinds of time series data. And a trend is something like you see over here. It's a change in the long-term mean of the series, right? So, obviously it's very simple, right? But how do you describe something like this? The way you describe it is, say, the mean in this part of the series is very different from the mean in this part of the series. So clearly there's an uptrend. There could be mixed trends. There could be uptrend and downtrend. But the important term here is the long-term mean. Because if your mean is long-term, and obviously this is data dependent, right? So first you need to look at the data and identify what a long-term mean means. But if your long-term isn't long enough, then actually what you see as a trend could actually be a seasonal effect. And a seasonal effect is also very common in time series data. So here is a graph of daily temperatures in Sydney, Australia. And you see it fluctuates, right? It goes up and down, because those are actual seasons, right? So summer is warm, winter is cold, right? So when we're describing seasonal data, the season or the period is the length of each cycle. So in this series, a season would be 1 year long. And if it was sampled monthly, actually it's sampled daily, I believe, in this one. So the length of the season in this data set is 365, right? And one interesting thing to note about seasons is seasonality can be additive or multiplicative. So by that I mean an additive seasonal effect, is one in which the seasonality is, there might be a trend as well, but the seasonality is constant, right? So this amplitude, you can call it, is constant across the series. But then you can also have a multiplicative seasonality, which looks like this. So maybe it'll start off small, the seasonality, but the seasonal variation increases. So there's different ways of modeling those two different kinds of seasonality. So as I said before, a series can have both trend and seasonal effects. So this is actually an interesting series. It's of airline passengers from 1949 to 1960. So you can kind of think about maybe how you'd interpret this. So obviously there's growth in number of airline passengers, so that's a trend. Also there's fluctuations, so maybe during holidays people are traveling more, so you see that fluctuation. But what's even more interesting is this fluctuation grows. So is this additive trend or a multiplicative trend? Multiplicative, right? Yeah. So that's an interesting effect. And later we'll think about how we would detrend the data and seasonal difference the data, which means take away the trend, take away the seasonal effects, and we'll see how to do that for additive and multiplicative. Yeah.
So isn't it both additive and multiplicative?
Depends. So it depends which portion you look at. Why would you say it's additive?
I'm seeing those two graphs. It's a mix of the.
Okay. I think you might be getting confused with the trend in seasonality. So just because it's increasing doesn't mean it's additive. This increasing effect is due to the trend. And there's clearly a trend here, right? There's an uptrend. But what I meant by additive and multiplicative is, does the variation in the season change? So maybe I just drew this badly, but I was trying to say like this variation in the season doesn't change. Like this season is the same as this season. Basically here clearly I tried to draw this. Like this season is bigger, seasonal effect is bigger than this seasonal effect, right? And then you can definitely see that in this graph. Is that clear to everyone? Any other questions? Yeah, cool. Time series is fun, right? Because you can visualize and you can make stories about what's happening. And time series is fun also because these concepts show up everywhere, right? So this is actually my workout app. It's called Map My Run. Do you guys use it? No one? Okay. You guys should work out with me. I go on some very fun seasonal workouts, as you can see. And this is actually from last weekend. I just did a run around Shenley Park. I ran, I think 2 or 3 times around Shenley Park. And I noticed after I pulled up the app, I noticed that my elevation had a nice seasonal pattern, right? So, went up, down, and then it's the same pattern again. And I thought that was really cool. So does anyone know why I saw a seasonal pattern in my elevation?
Because Shenley Park itself is in a slope.
You're doing the same thing again and again.
Yeah, that's right. I ran the same thing twice. Right. So maybe not a very inspiring time series data, but I don't know, inspiring for me. I liked it. Yeah. Cool. So now that we've talked about dependence, trend, and seasonality, and seen some examples of that, we can talk about a concept called stationarity. And basically this concept says that a time series is called stationary if any one section of the time series, any one block of the time series, looks like any other block of the time series in terms of the distribution. So it doesn't have to be exactly the same values, but the distribution of those values have to be similar, right? So what does that mean? So if you had a series like this is called a white noise series. And what a white noise series means, it sounds very complicated, but it's actually really, really simple. It's just a series of random values. So this plot I generated by sampling from a Gaussian distribution with mean 0 and standard deviation 1. And what you'll notice is, any section of this series looks just like any other section in terms of distribution, right? And what that means is that the series is stationary. So white noise series is actually stationary, and you can actually prove that. But why is this important? So it's important because typically, your data is dependent, and dependent data typically is not stationary. Again, stationary is also important because, we'll come back to this later. Stationary is important because many of the time series models we'll be using will assume that your data is stationary, right? So we have to take actions like detrending the data, removing the seasonal effects to get it first to this state, right? And then once we get it to this state, then we can start the modeling process. Right. So quick question, is this series stationary? This is the same as Japan, the one we saw earlier, trend. No, right, because there is a trend, right? So that's pretty clear. So series that have trends are not stationary. Is this one stationary?
Yes.
So who thinks it's stationary and wants to make an argument? Yeah.
Because a pattern is repeating again and again. That's why it's stationary.
Pattern is definitely, yeah. So you see the seasonal pattern repeating. Okay, but who thinks it's not stationary? Ian, do you want to say why?
The peaks look different than the valleys, I would say.
Yeah, pretty much. So, there's definitely a repeating pattern, and that's a seasonality. But you see, let's say I grabbed some arbitrary sections of the data. I said, to be stationary, 2 arbitrary sections have to look the same, right? So I can make up a section, say this section of the data. Sections have to be of the same length. So this section of the data is the peak, right? So it has very high values. But then this section of the data is the value, has very low values, right? So the distribution of those two sections is different. And that's why we say like, this series is not stationary. So typically, if there's series with seasonality, it won't be stationary. So as I was saying before, it's important to understand the concept of stationarity is because often you want to get your data to a stationary state, right? So let's say, again, we looked at this airline passengers data set, the series, and obviously it's non-stationary. What we can do is we can first remove the trend. So we remove the trend, and don't worry about how this is happening. I'll explain later like how we're actually doing this. But if you actually remove the trend, one way you can think about it is just we can fit a line here, and then we subtract these values, the series values from that line. And the residual that we get is actually this detrended series. So this is our first pass at trying to make it stationary. But is it stationary yet? No, because the same problem as before, because it has these peaks and valleys. It's seasonal, and seasonal data isn't stationary. So let's take the next step, which is to remove the stationarity, right? And this is another method called seasonal differencing, and we'll talk about this later. And once you remove that seasonality component, what we get are the residuals, right? And these residuals, at least right now, it looks like it looks kind of like white noise, right? And that that is stationary. But one interesting thing you'll notice is that actually there's some change in variance here, right? So it seems like here, not much change in variance, but then suddenly the variance of the series, like the spread of the series suddenly increases, right? So this is actually an issue, and maybe we can talk about this later, because the stationary series should have the same mean throughout the series, and should also have the same variance, right? But here this is an issue, which probably means we should go back and do the seasonal difference incorrectly, right? So the reason this is probably happening is because you can see in the seasonality plot, right? In the detrended plot where you see the seasonality, the variance is actually increasing. And this is happening because of the multiplicative seasonality, right? So we might have to do another approach at differencing, maybe a second order differencing to get it truly to be stationary. But we'll say for now, this is approximately stationary. Okay? Cool. So that's it for stationarity. Any questions about this concept? Okay. Yeah.
In this graph, there are also peaks and lows. And in the previous one, also there were peaks and lows. So why that is not stationary, why this is stationary?
Does anyone want to try to explain that? Yeah,
It's
Sean?
sort of like related to some sort of like hypothesis test. Like given the picture there on the far right, like I couldn't confidently say that it's not just drawn from a Gaussian distribution, and that there's like some consistent pattern.
Yeah, so that's fair enough. There's actually, so how do you actually test this and say whether or not, this is stationary or not? And that's like the question you're kind of bringing up, right? Like this kind of looks like it has a seasonal pattern, right? So I'll get to both of those things, but first your point is there a statistical test? And yes, there is a statistical test. It's called the Dickey-Fuller test, and that is a test of stationarity. So the null hypothesis there is that the series is non-stationary, and you can get a test statistic for this, and then see if it's less than the p-value, and then you can see whether it's actually stationary or not. But there's a whole host of issues with p-values and hypothesis testing, so I didn't want to include that. But often, just by looking at the series, you'll be able to tell, and once you've done the differencing, you'll be able to tell whether it's stationary or not. So now getting back to your point, whether there's seasonal effect in this. So I'd argue actually that there's not a seasonal effect here, right? There definitely seems to be random variations, right? So some spikes and falls, right? But it's not a seasonal effect of fixed length. So if you remember how we define seasonality, seasonality has to be a cyclic pattern of a fixed period, right? So here we see like the period is obviously 1 year long, yeah. but here, can you tell me what the seasonal length is here? You really can't, right? So that's why we wouldn't say this has seasonality. Okay. Which is actually an interesting point because there's a concept of cyclical data, so there are cycles in your data. So for example, consider economic cycle, right? So economy sometimes doing great, sometimes not doing that great, but it's actually not a seasonal pattern because, economists don't know, like, okay, how long does a cycle take? So that's a cycle. But a seasonal pattern is what we described before, like, the length beforehand. It's a fixed length seasonal pattern. Yeah. Cool. Okay, so now that you've got introduced to some of the basic theory of time series, we can talk about some cool applications and an example that we'll be using. So there are 4 main applications of time series modeling. So there are description, forecasting, explanation, and control. So let's go through each of those. So the first one, and actually this is one of my favorites because you can actually see everything. It looks very nice. First one is description. And in description, we ask the question, can we identify, measure, and possibly remove the trend and seasonal components in the data? Can we figure out where the outliers are? Can we figure out if there's missing data, right? And before you go into any of the other steps in time series analysis, you should always go through this description stage. So as I said, can we take out the trend component from this time series, right? So time series, we take out the trend component, take out the seasonal component. So that's what description deals with. And description is nice is because, if you have, maybe you're working with some client, before you actually get to the modeling phase, before you, make some forecasts, you can make an effort to describe the data that you have and explain, all right, here's my trend of variable of interest, here's the seasonal pattern. If you notice that there are some holes in the data, right, which is very common, you can go ask, like, hey, this variable isn't being measured, or this variable has, such missing values, or is not being measured accurately, right? So this description stage is very important. The second application of time series is explanation. So this explanation, how it works, let's say you have 2 time series, they could be maybe correlated time series, and you're trying to use one series to predict another, okay? And we won't be covering this today, but basically there's this concept of linear systems, which over a time period, so they'll take an input series, apply some linear operations, linear combinations, and then output this output series. And that's the approach there. There's also this domain of statistical control. This problem, how it's set up, is let's say you're observing some metric over time, maybe it's some performance metric at, say, you have a manufacturing plant, and you're trying to assure some level of quality, right? So you have some target for that metric, and you also have some upper and lower bounds. And your goal is to figure out, when your time series is off target, so that you can make adjustments and get it back to target. And this is actually very closely related to our next problem, which is forecasting. Because the idea here is, if you can forecast ahead of time, which machine is failing, right, or which engine needs repair, right, then you can take corrective actions immediately, right? So one of the focus of our lecture today will be forecasting, which is the question of using observed values, can we predict future values of a time series? And this is actually very similar to some of the stuff that you guys have been doing in class and in the homeworks, right? But now I've added this time component to it, right? So suddenly you have to deal with time. So that makes it very interesting. Any questions about these applications? Okay. Yeah, so in today's lecture we'll focus on the description and forecasting parts. And what we'll do is we'll motivate our time series analysis discussion with this very interesting problem. So this problem is, the data set is called the Keeling curve. And this curve, this data set is the foundation of modern climate change research, right? And so what it basically is there's this observatory in Hawaii, so a nice place to be a scientist, probably. And yeah, hopefully better than Pittsburgh. But what they do is since 1958, they've been taking daily CO2 observations, right? So it's in this mountaintop. It's completely undisturbed, right? There's no pollution over there, no human activity. And they've been taking daily observations of CO2 concentrations. And what they found is, this is not since 1958, this is in 1989. They found this series, right? And this is known as the Keeling curve. So this is kind of surprising, maybe, kind of scary. The CO2 emissions is going up, that's a greenhouse gas. But it's also a very interesting time series problem, right? Because what if you can forecast this into the future, right? So maybe then you can inform policymakers, and maybe they would act or maybe not. And it's interesting because I haven't showed how this curve extrapolates in this direction, right? But since the Industrial Revolution, since the start of this human industrial activity, this curve has shot up, and it's commonly referred to as the hockey stick curve, which is also an interesting phenomenon because if that happens, how do we even forecast something like this, right? So it's an interesting question about time series forecasting is with the uncertainty that's there, can we really make long-term predictions or can we not? But anyways, those are big questions. We can get back to some simpler questions now. So some interesting questions are, why is there an annual season here? So the season, this length here, is 1 year. So why do you think there is an annual season?
The plants spring up and consume the carbon dioxide.
Yeah, that's it. Are you an environmentalist or do you believe in climate change? So maybe then you can answer the next question as well.
Because it's rising.
Because
of climate change.
yeah. Yeah. So it's really interesting how, these same concepts we've talked about before, trends and seasonality, they relate to real life phenomenon in this case, right? So you see the climate change, that's an uptrend. And you see, this plants growing in the spring, dying in the fall, and it's causing this seasonality. Well, I can't say it's actually causing it. Let scientists say it is, so I'll assume that's true. Yeah.
Yeah, I'm just curious, where'd you get this curve from, this graph?
This is publicly available, so in my notes I'll share the link to the data set. But it's actually a super fascinating graph, especially if you extrapolate in that direction. Yeah, and I don't even want to think about what happens if you extrapolate in
What
that
happens
direction.
if you extrapolate in that direction?
Actually, yeah, we might as well see. Extrapolate meaning looking at the historical values. Yeah. I have a bookmark.
I think it's
What's that? Okay, yeah, here's a short video. Alright, so that's what we saw. It's the ice core data. This is when they drill into the ice to look at historical CO2 emissions. Oh, and it seems like a seasonal pattern here too. So there's a little dose of reality. Any other questions or thoughts about this one? All right. So then let's continue and let's figure out how to describe and model this thing. So the first thing you should do in any sort of time series analysis is take a descriptive approach, right? And use descriptive methods to figure out the important properties in your series. And the easiest way to do that is obviously through visualizing it, right? So once you visualize the series, you'll be able to see, whether there's a trend, seasonality, outliers. One interesting thing is that there's some missing data here as well. I didn't show it, but after visualizing, I saw okay, there's definitely some missing parts when the data was starting to get collected in 1958, 1960. So I was able to remove those observations, right? But if there's missing data in the middle of the series, that's up to you to make a decision, like what do you want to do about it, right? Do you want to impute those values through like some mean imputation? Do you want to interpolate those values based on surrounding points? So these are really important questions to answer before you get to any kind of analysis. But once we've done that, let's discuss how to extract these salient features from the time series plot, right? So things such as trend and seasonality. Once you have a time series, right? Once you have this original series, how do you measure the trend of the series? Does anyone have any ideas?
And you just average up all the values.
Yeah, that's definitely one approach. That's the one we'll be discussing. Yeah.
I was gonna say average the differences, but.
Average the
Like
differences.
between consecutive ones, so like if it's increasing by linearly,
Mhm.
then like the average difference between consecutive values would be positive.
Average difference. That might work. So that actually ties more into the concept of detrending and getting this seasonality out, and we'll also be looking at that. But that's something to think about. If averaging the differences would also work as well. The differencing is actually what will detrend the data. Yeah. Any other thoughts?
Isn't this similar to what we do in neural networks? For example, moving averages, that when you go towards the minimum, something like that, moving average?
Yeah. So moving average is the approach that we'll
Like
talk
80%,
about.
yeah.
But another simpler way is why don't you just like fit a line to this data? So you can fit a line and then you have the trend. The issue with that is like, this here the trend is linear. Oftentimes the trend won't be linear, right? And then fitting a line won't work. So instead what we do is we use a moving average, right? And the moving average, this should look, maybe it's familiar to you, maybe some bad nightmares about this. You guys know what I'm talking about. Sliding average, right? So homework question. Obviously our version of, our class's version of sliding average is much harder, right? Because you have to make it super efficient. But, the sliding average, moving average is very simple, right? So you just, as you go over these sections, you have some window. You're going over the series, you just average the points at each section. And with the sliding average, this is actually a sliding average of the series we saw before, the Killen curve. You can see, you definitely see the uptrend. This is how you do it in Python. So in pandas, there's a function called rolling, which basically takes windows of your data. So here I say, slide windows of size 12 over the data and compute the mean, right? And I use 12 because, again, this is where the long-term mean comes in, right? What is the long-term mean here? So I thought, maybe since the seasonal period is 12, right? 12 months. What I do is I'll just average over the 12 months, a year. And that's long-term enough for this one, this data set. Right, so then we can measure the seasonal, or the non-seasonal trend, and then you can present to someone, right? And you can say like, okay, this is the rate at which CO2 emissions concentrations are rising, right? And this can have, very powerful effect, a very powerful impact, but also very easy to understand, right? So now, once we measure the trend, how can we remove this trend, right? So one obvious way of doing it is you just subtract the original series from the trend. Another approach, which might be even simpler, in which you don't even have to compute this trend explicitly in the first place, is just by differencing the series. And how differencing works is each point you subtract it with the previous point. Yeah. And surprisingly, this gives you a detrended series. So you can do this detrending, this differencing in different orders. So this is a first order difference. There's also a second order difference. So if you notice that, okay, you detrended your series, but it doesn't look, it still looks like it has some trend. You can take the first difference and then subtract it with a second level difference. And you can look at that later, but it's a very similar concept. And what this relates to, this is really like taking a discrete derivative, right? It's just the change in values over the time, right? And the result you can get from this by detrending is you remove the trend out of the original series. So what I did, I took this original series and I did the detrending, and this is my result. So you see the trend is gone now, but what's left? The seasonality, right? This is how you do it in Python. Again, pandas is very nice. So if we just do diff, right, your series dot diff, it automatically computes the first order differences. And in the diff, if you want to do a second order difference, you can also specify some period, and that'll let you do, higher order differences, right? But usually for most cases in practice, first order differencing is enough. Sometimes if you still see some trend, you might want to do a second order differencing. Now, why am I even talking about these concepts, right? Like, why would you ever want to remove a trend from a series or a seasonality from a series? It may not be very obvious here. It's obvious why you'd want to measure a trend, right? Or measure seasonality. But we discussed removing the trend is because this is a prerequisite for applying our models, right? Our models assume that our time series is stationary, so we have to get it to the state before we can apply the models, right? So just so you guys can see how it works and how you'd implement it. And similarly, we can also think about removing seasonality, right? How would you measure seasonality, by the way? Measuring seasonality is like, just like this, right? If you have a defended plot, by effect, what you're doing is you're just seeing the seasonal effect. That's what's left over. So that's why I'm not talking about how you would be measuring the seasonality. Right? Did anyone have a question here? I think John.
If you wanted to show somebody that hey, it's seasonal with this period, would you plot the each point against the point that came m steps before it? So like if there is a period there, then you'll have like a perfect line.
Yeah, that's actually another way to do it. And that's also the concept of seasonal differencing, right?
Okay,
Which
yeah.
we're going to talk about next. But yeah, you're doing very good. You're getting ahead of me. But you can definitely do that, and that's exactly what you get. Yeah.
How do you know the trends and seasonality are removed? Like the data is good enough to assume stationality? Do we need to run the test every time?
Yeah, you can run the Dickey-Fuller test, but obviously, if you run it every single time, right, you have this issue of multiple testing issues, right, which is the concept of in hypothesis testing, right? So if you have a 95% confidence interval, right, alpha of 0.05 in hypothesis test, and then if you run it 20 times, at least one time it'll just be a false positive, right? So there's you have to be very cautious when you're doing a statistical test, but you can definitely do it. You can definitely do a Dickey-Fuller test.
Then what's the kind of good method to determine like my data is good enough to run, the other models that I want to apply? Do I just is like looking at plots?
Plots is definitely good, right?
That's
Positive, but yes, you can definitely run the statistical test, and if you see, that if you can reject null hypothesis, right, then that means for the Dickey-Fuller test, that means your data is probably stationary, and then you can use that. Yeah, John.
This is getting kind of crazy, but if I guess if you want to come up with an automatic way to select the appropriate period,
Mm-hmm.
would you I don't know plot the Fourier transform of all I know is electrical engineers deal with this, so they know more about it than I do, but
Yeah, that's actually also a great point, because one thing I didn't mention before is that there are two approaches to this time series modeling, right? One which we talk about here, which are time domain approaches, right? So the domain here is actually just time. There's also, if you study electrical engineering or signal processing, there's a frequency domain approach that deals with things like spectral density functions, right? So essentially that approach is about modeling this variation in data using sine and cosines, combinations of sine and cosines, right? And that's a Fourier series, right? And that extends to Fourier transforms. I honestly don't know too much about that area, but that's definitely also another approach. But that's also a good question. How would, if you didn't know beforehand, how would you find the period, right? What is this length of the season? So that's something definitely to think about. Okay, so going back to seasonality, we'll do what John suggested, which is the seasonal difference, right? And seasonal difference is nothing else but you take the current point and you subtract it with the point one period ago, right? Very similar to removing the trend, the trend differencing, the first order differencing. But first order differencing, right? You just, let's say this point, right? You would subtract it with this point here, right? So if that, those are 2 time steps. But seasonal differencing, the concept is if you have this point, you subtract it with the point at the same point in the previous season, right? So let's look over that. And this is how you would implement it, right? So it's, you know, just the same code, except now we're not using the original series. We're taking the detrended series. We're first detrending. We're taking this series, and we're doing seasonal differencing on that to get rid of the seasonality. Okay. And what we get is this. So it looks like, you know, there's no fixed length seasonal pattern, and, you know, it just looks like a whole lot of white noise. And then just by looking at it, you know, you say, you know, it's good enough, it looks stationary. And then if you want, you can go ahead and try some statistical tests to confirm that. Cool. So now we're moving on to our final section about forecasting. And I know this is what you guys have all been waiting for, you know, can we predict the scaling curve and see if humanity is doomed or not? But yeah, so yeah, this is my estimate at first. This is what I thought it would be. I just made it, but I don't know, maybe that's conservative, but we'll see. But you know, just by looking at this plot, right, you think it should be pretty easy to forecast this. It looks pretty simple, right? So then, you know, why all this hype, right? It's why, you know, who cares? Just time series, right? But it turns out that we can't really use, you know, simple linear regression to model this, right? And there are a few reasons for that, and that's why we'll be looking at some variations of linear regression. So let me kind of explain why you can't do just a, you know, a linear regression. So does someone have any ideas why that would be?
You're assuming that the trend would, you would basically assume that there's no change in the trend. That you're maintaining a constant rate of increase or decrease.
Yeah, and so fair enough. And that's a good point. So what if you actually had the Japanese automobile data, right? Which looks like this. So it maybe has some exponential rise. So maybe you know, linear regression model wouldn't be a good fit to this. But then, you know, in class you learned about some linear regression model with polynomial features, right? In which we can, you know, use linear regression to estimate not just lines, not just straight lines, but curves, right? So potentially, right, we can model that. Right? But the issue with linear regression is actually with the seasonality. So if you have a seasonal effect like this, and let's say you fit a line to that data, right? So obviously a line isn't a good model, right, to fit this data. But even if you use some polynomial features, right, or you have some RBF features, maybe we have a very high degree polynomial, right? And the high degree polynomial can fit this data really nicely. If you remember, this is very similar to what Zico showed with the electricity demand prediction, right, where we had, you know, some really weird curves, and you can actually fit that. But the issue with that is that you'll have some overfitting issues, right? Because when you extend this high degree polynomial, right, it won't follow the seasonal pattern, right? So if you extend it this way, it'll keep going up. Whereas there's actually some actual seasonal pattern, right? So you expect the actual values to go down. And that's because this linear regression model, simple linear regression model, has no idea of the seasonal component, right? If you remember what I said before, that any sort of time series analysis has to take into account the time order of the observations, right? if you just look at time as some independent variable, right, it won't work. So let me compare that to a case where linear regression would be fine, right? Let's say we have some points. Right? Obviously we can fit a line through this. But the assumption here is the points are independent, right? Independently sampled. So it's not like this point comes before this point, which comes before this point, right? There is no ordering of these points. So there is no sort of dependent structure between each point that we have to capture. And that's why we can use a time series model there, a linear regression model there, but not here. Okay. Does that make sense? Are there any questions about that? Yeah.
I mean, couldn't you just use a linear regression model in the time series data, but like use rather than polynomials, use like a sine or cosine with a period based on what you observe the seasonality.
Actually, I think you can do that. We had a similar approach, if you remember, a few homeworks back,
Yes.
where we were trying to predict bus arrival times, right, ETAs, and then one of the variables was actually time, right? And we did a sine and cosine transformation. So that's actually a different concept. We did that transformation then because obviously, like time, right? So if you think about time in hours, right? You have 1 to 24 hours, but it's not like hour 24 is much different than hour 1, right? Because it's a cycle, right? So after 24, you'll get hour 1. So that's why we did that. But I can imagine, yeah, there would be some variations you can do of linear regression, simple linear regression, where you can have some, sine and cosine terms to actually model this seasonality as well. Yeah. But what we'll be focusing on is another variant of linear regression called an autoregressive model. And that will be the basic building block of our approach. Okay? So now we'll start talking about this set of models called the ARIMA models. And they're by far the most popular models in time series forecasting. And what ARIMA is this family of models, right? They're based on autocorrelations of the data. Autocorrelations meaning how correlated are the successive observations, right? So they're highly correlated, right? That means they're dependent, and you can use one observation to predict the next, or to predict some sequence into the future. And there are 4 main models in the family. So one is called an autoregressive model, AR, a moving average model, ARIMA, which is autoregressive integrated moving average model, and it just combines these two. That's what it is. And then finally, you have the big brother of them all is SARIMA. I just made that up, but I think that's how it's pronounced. SARIMA is maybe I should just call it seasonal ARIMA. I don't know. I'll just call it SARIMA. It's okay. So SARIMA is just a seasonal variant of ARIMA. And what we'll do is we'll start out with the basic building blocks, and we'll start talking about the autoregressive model first, which is most similar to the linear regression that we've seen. Has anyone seen autoregressive models before? Okay, yeah. So I think autoregressive models is a very cool concept, because you can take the same kind of theory and intuition you apply for linear regression and extend it to an autoregressive model, right? And you should notice this should look very similar to your to a linear model, right? To a linear regression model. You have some coefficients, you have some bias term, and through a linear combination of the features and the coefficients, you can predict the next value. So here what this is saying is an autoregressive model predicts the value at xt by some linear combination of the previous values, so t minus 1, t minus 2, all the way up to t minus p. Okay? So if you think about what this would look like, is maybe I'm trying to predict this point here, but I'll use some points, p time steps before to predict it. So maybe 1, 2, 3, 4, 5. So there maybe p equals 5. And I'll look at those points and I'll apply some linear operation, and through that linear combination I'll get my prediction. So the idea is you want to learn these parameters, theta 0 to theta p, that help best fit the model to that data, to the xt. Okay? Does that make sense? Yeah, it's just your model contains, you're modeling the current value based on current observation based on previous observations. Yeah. And in the linear regression setting, you can do this exactly by using a linear regression model. And all this is a linear regression with lagged features. So let's say this is your original time series plot. And when we're doing machine learning, we have to set up some features and some labels, right? So here we can think about how to set up our features. This is also known as the design matrix, so that we can have an autoregressive model, right? And how you do that is just by using lagged values, right? So for the first two observations, we won't have any observation in this design matrix because we don't have any p observations before. We're assuming here p equals 2. But here, right, for this observation, third observation, we'll say this is our variable of interest. We're trying to predict this. And we used observation 500, this one, 2 and 1, in this row of the matrix, right? So 500, 400. And then when we look at this next observation, 100, so this is what we're predicting, our response variable. And we look at the previous two values, 300, 500. And then finally we have value 200. And we look at the two values before it, 100 and 300. So each feature here, so let's say this is the label, this is the point you want to predict. And each feature is just a lagged predictor, a lagged observation. Okay. Does that make sense? Yeah.
So this, like, it's possible to get the moving average out of an AR if, like we said, like, theta 0 to be 0 and then the rest of the theta to be the same value.
Yeah, exactly. So this is exactly the moving average in the case where all the thetas are the same and they sum up to 1. That's exactly what this is. But the key here is, moving average is kind of dumb, right? Because you're just setting all of these thetas equal to each other. This is smarter, smarter because all of the thetas, you're learning the values of the thetas to best fit the data. Okay. Cool. So now we talked about this model, AR, autoregressive model. The second type of model in ARIMA is known as the moving average model. The moving average model is a bit more blurry because what it says is we're going to model the value of interest to the response using a linear combination of the previous errors of the model, right? So you can think about, you're using this autoregressive model to make some forecasts, make some prediction. And then for each time step, you'll get some errors, right? And you also want your model to kind of incorporate the kind of error that you're getting, right? So what these epsilon terms are is they're just like white noise, right? And they correspond to errors in your forecast. And now instead of the forecasted value, the predicted value being a linear combination of the lagged features, this is now a linear combination of the lagged errors of your forecast. Okay, so this by itself may not really make sense, but when it starts making sense is when you combine it with AR, and we combine AR autoregressive model. So when you combine the autoregressive model and moving average model, what you get is the ARIMA model. Okay. And before we move on to the ARIMA model, one thing I just want to clarify is you pay real close attention to these parameters here. So in autoregressive model, we had a parameter P. Okay, so that's a number of lag predictors that you're using. How many time steps in the past are you using? In the moving average model, we have parameter Q, which is the number of past errors that you're using. This is important because the same parameters show up in the ARIMA model, autoregressive integrated moving average model, and they have the same kind of concept. Okay. So all an ARIMA is, yeah, John?
So on the previous slide, were the errors for the moving average model itself, or like a different model? Like this is sort of an adjustment like on top of the other model. Okay, I don't know if that sentence made any sense.
Yeah, no, I know. This is actually a very confusing topic. I know I was having trouble when I was reading it before, and still, it doesn't make complete sense to me. But from what I understand, right, the model is that the errors is distributed as white noise. But in effect, what it's doing, white noise meaning just like, random errors, randomly distributed errors. But in effect, what it's doing is actually it's using the previous errors in the forecast to make predictions of the future.
But this forecast is from the moving average model itself. Like, is it like crazily recursively defined, or?
Yeah, so it's somehow related to moving average. I'm not 100% clear on that, but something you might want to look into. The moving average model, yeah. So what's interesting is that we can combine the autoregressive part, AR, and moving average part to create this ARIMA model. And this looks complicated, but all it is really is, this is the autoregressive part, and this is the moving average part. And now you just have a big, complicated model, right? So now that we have this model, right, it's framed as autoregressive part and moving average part, one thing we want to make sure is that our data is stationary. So we want to come back to this concept of stationarity, right? And then how do we do that? So one thing we can do is we can manually make sure that data is stationary. We can take out the trend, we can take out seasonality. But the cool thing about the autoregressive model is that it makes a forecast of the detrended values, right? So this xt prime here, this actually refers to the difference series. And do you guys remember what the difference series is? Like, what is first order difference? So if you take a first order difference of the series, what will that give you? So it will give you the trend.
Removing the trend?
Sorry, yeah. It'll give you, it'll help remove the trend, right? That's correct. So it'll give you the detrended values. So here what this model, ARIMA model does is you can automatically make it detrend the values, right? And how you do that is by setting this D parameter. Okay? So if you already have stationary data, maybe it's already stationary or you've detrended the data yourself, then you can set D equal to 0 and it'll be fine. But if you have non-stationary data, you see it as a trend, then you should set D equal to 1 for first order differencing or D equal to 2 for second order differencing. And yeah, so in that case, your ARIMA model is parameterized by 3 parameters now. P, which is the order of the AR model, Q, which is the order of the MA model, and D, which is your order of differencing. Okay, so I know this is confusing, and I think one thing I should add here is this is not for seasonal data, right? Because if you throw in seasonal data to this model, why do you think it won't work?
Because it's not auto-correlated with the point immediately, its immediate neighbors, essentially. It's more.
So it definitely is. If you have seasonal data, right? So there's definitely, and I know I didn't explain the concept of autocorrelation, but autocorrelation is just the concept where, let's say you have successive operations, right? So are these two correlated, right? Then are these two correlated, right? So there'll definitely be some correlation, right? At least for some distances. But the reason why you can't throw seasonal data at this model is because it doesn't really do any seasonal differencing, right? So remember, before we use any of these models, we want to make sure our data is stationary, right? And if you remember, I said you can throw some data at this model. It might not be detrended, but the fact that this fork has detrended values, and you can set the detrending of this differencing parameter, you can take care of that problem, right? But if you have a seasonal pattern, right? If you have a seasonal data, what you'll actually get is even after the ARIMA does the detrending, you will get something like this, right? This will be your data, and it will still have the still have the seasonality, and it won't be stationary. So that's the reason why we'll talk about the final variant of the ARIMA model, which is a seasonal ARIMA model. Okay? And I didn't write out the seasonal ARIMA function because it's very complicated, it's very big. And it's very similar to the ARIMA model. Except what it is here in the ARIMA model, you had one line, one moving average model, one average outer regressive model. And in this, what you'll have is there'll be two components. So you'll have one which is a non-seasonal component, which is the same as ARIMA. Right? So ARIMA is a model for modeling non-seasonal data. And then just like that, you'll have another seasonal component. And this seasonal component, the main difference here, is that you'll have a different seasonal differencing parameter. So just like we did differencing here to do the detrending, right? ARIMA has another parameter to do the seasonal differencing. And that parameter is called D, capital D. So this lowercase d refers to the differencing parameter, the first order or second order differencing. Uppercase D refers to the seasonal differencing parameter. So now in this model, if you want to do no seasonal differencing, maybe there is no seasonality in your data, or you've already taken it out, you can set the D equal to 0, and it'll be totally fine. If maybe you've detrended the data, or if you haven't detrended the data, and you see there's still some seasonality, you can set D equal to 1. You can set this D equal to 1 as well, if you want to remove the trend and seasonality. Yeah?
In ARIMA, it doesn't remove seasonal, right?
It doesn't.
Okay.
So, and again, it's because to remove seasonal effect, what do you have to do? Do you remember?
Yeah, the same thing. Seasonal difference.
Seasonal differencing. So you do difference not with the previous point, but with the point one period ago, right? The issue with ARIMA is it only does differencing, right? So it does remove the trend, but it doesn't remove seasonality.
Is the only way to remove seasonality to remove the trend first? And I mean, to isolate the trend without the seasonality, would you just remove the trend, remove the seasonality, then add the trend back in?
Yeah, so I'm actually not 100% sure on that. I think the ordering won't really matter. So you can detrend first and then deseasonalize. And it should be very similar to deseasonalizing and detrending. But I think that's something I'll leave up to you to look up. Right? I think that's what you're asking, right? Does it matter which one you do first?
I mean, that's part of it, yeah.
Yeah, so the answer is I'm not very sure. Yeah, but I've seen it done both ways. I've seen people first remove this seasonality and then remove the trend, and they get some non-stationary plot. Yeah.
Can this be done on the categorical data as well?
Categorical data. So to predict categorical labels, is it? Yeah. So then it wouldn't be a regression setting anymore. But there are these things called state space models. And the good thing is the same, before we talked about forecasting, the same concepts we talked about, same core concepts still apply. But there is a different class of models for that. One of them I recommend you look at is called hidden Markov model. And you can use that to forecast categorical labels. Yeah. And you can see why that would be an interesting problem, right? But for our setting, we're just talking about forecasting continuous value data. Yeah. So then going back to the previous question, ARIMA doesn't capture seasonality because it doesn't do the seasonal differencing. ARIMA though will do the seasonal differencing if you set D, this capital D equal to non-zero. Okay. We already talked about what the P, D, Q parameters are for the ARIMA model. And for the ARIMA model, obviously those are the same as it was in ARIMA. And this capital P and capital Q, they are basically the seasonal analogs of what you saw in the ARIMA model. So P in this case is for the seasonal part of this model. How many lag predictors do you use? How far back do you go? For Q in this model, for capital Q, it says for the seasonal part of this model, how many lagged errors do you look at? Yeah. So I know this is very confusing. There's like some 6 parameters. There's this non-seasonal, seasonal part. But basically what it comes down to is a linear model that takes into account some non-seasonal component and some seasonal component. Another question is like, okay, so at least you've framed this and defined this model. How do you go about estimating the parameters? At least these hyperparameters, right? Like PDQ, capital PDQ, and M. So the good thing is M you already know, right? M is the seasonal period of the data. As I said, the capital D, lowercase d are, you can just by looking at the data, you can see if it needs some detrending or it needs some seasonal differencing. So you guys understand that, right? Like how we do M, how we get M, D, and uppercase D. The big question is like, how do you get the P's and Q's, right? How do you know how far back you want to look at to predict this next point? Or how far along the spectrum you want to consider errors, right? How many errors you want to consider. And there's really no straight answer to that. So there's techniques of looking at the autocorrelation and partial autocorrelation functions. So these are functions, maybe if you're interested, you can look into this later. They're functions and you can basically understand how successive observations are correlated, how correlated are successive operations. And there are techniques of using those plots to determine what P and Q parameters you should use. But in practice, really what you can do is just use a grid search. So you can have some candidate values. Like we all remember a grid search, right, from class. I think you guys are doing it in the homework as well. So you have some grid of values for these 4 parameters, and maybe even for the D parameters. And then you just search over the space. You fit a model for every single possible combination of these parameters, and you evaluate its performance, right? And you can do, basically the cross-validation that we've been doing, right? So you can hold out some validation set, fit your model on your training set, and then keep evaluating on the validation set and see how your performance is. Yeah. And there's various performance metrics you can use, but typically when you're dealing with time series data, what's used is called AIC, which is I think it's a Kaike information criterion. And what this does is it balances the complexity of the model with the performance of the model. So if you guys remember when, in machine learning and statistics, we want to have models that are good fit to the data, have a high performance, but are also simple so that they can generalize well to new unseen data. And this is a metric that balances that. It's similar to regularization, right? So you can have some regularization term in your model and that will control the complexity. But in this time series models, we don't really have an explicit regularization parameter. So we deal with it by minimizing the AIC. Cool. So any questions here? Now, next I'll actually show you an interesting part, which is fitting the model. Yeah?
So in the like non-time series setting, we often have like a independent test set, which we could especially for classification, we could just count the number of times that we got the label right, and then that would give us a metric for how we assess our model.
Mm-hmm.
But we can't really. How can we make the same? Is there an easy, simple, straightforward way to make the same independence assumptions here? With because if I have a really enormous model, and I'm just trying to forecast some chunk that comes afterwards.
Yeah.
I think I can boost that forecasting accuracy by just making my model bigger and bigger and bigger. I think.
That's a fair point, but you might actually lose. So that's actually a decent point. So you might get a better estimate, right? If you look at more and more data, or you might not if the data that's closer to your predicted point is more important, right? So their approaches, one is called exponential smoothing, also known as ETS. They'll look at an entire data, a section of data to predict the next point. But what it does is it does some exponential weighting, right? So as you go closer to your forecasted point, you will increase. There's people waiting.
We have the room for
Yeah,
exam review session.
Okay.
Next 2 hours. But,
We'll wrap up in 5 minutes. Are you okay with that?
Yeah, we have a lot of students, so if you make that.
Okay, we'll make it
There are a
good.
lot of people. and-
Okay, let's just get through this, and these notes will be up online, so we'll finish it real fast. Cool. So how do you actually go about implementing this model? So you have this data frame, let's say, and you're trying to predict the CO2 values using the date. Here's the code, right? So we use a library called stats models. It's in Python, and we can fit a Surima model just like this. So you have some PDQ parameters. You have some capital PDQ parameters with the seasonal order. The caption will give you some output, so you'll be able to see what is the coefficient of each of these parameters, what is the standard error, right? So this is just your model. And from this model, you'll be able to create your forecast. So in fact, you'll be able to both create point predictions for your forecast as well as confidence intervals. And then, once you plot that forecast, you'll get a nice ARIMA model forecast. Right. And you see I've also plotted the confidence intervals as well, along with the point observations. Cool. So that's it for today. We went over some of the basics of time series models and also discussed one approach to forecasting them. But you might also be interested in other things. As John mentioned, there's a whole frequency domain methods of forecasting. There's also new neural network models, such as RNN, for modeling sequential data. That's something to look into. Cool. These notes will be up online. Thank you.
Thank you.
Yeah. Actually, I can use that.